In this next topic, we will briefly cover voltage operating limits. The objectives are for you to be able to describe the impacts of low voltages, describe the impacts of high voltages, and also describe how voltage limits are applied for a major large reliability coordinator. So when we have low voltages, there can be impacts on the motor loads. In the range of 90 to 100%, those loads basically operate as constant power devices. They're dependent a lot more on the frequency. So if we're driving a fan, or we've got an induction motor driving a large industrial facility, as long as the frequency is constant, the demand of that load is a function of the speed. So as the voltage drops, the speed stays the same, the power stays the same, so the current has to pick up to take advantage of that. So as the voltage drops down, the current picks up. But as we get to very low voltages, like 70%, those motors can actually stall. And as they come to and they slow down, they can actually create very high reactive demands at that point. And then as they recover, they also have a large inrush current. So we really have to make sure that we keep the voltages well above that range to avoid motor stalling and consequent damage to, you can imagine that you've got a steel mill or you've got a large industrial plant. When those motors are stalling, everything comes to a dead stop and you can have tremendous disruption of that plant. Now, with non-motor load, that tends to be more voltage sensitive, and so as the voltage drops, particularly like with lighting, like incandescent lighting, basically that varies as the square of voltage. Heating elements vary with the square of voltage, and fluorescent lights are pretty much linear with the voltage. So we can have either constant impedance loads or constant current loads. As the voltage drops in that particular case, the load also drops. And as a rule of thumb, if the voltage drops by 5%, the load will be down around about 6%. If it was purely resistive, as the voltage dropped by 5%, our load would be dropping by about 10%. But because we have a combination of fluorescent lights, which are more linear, versus the incandescent lights, then it's about 6% for the 5% voltage drop. Now, when we combine both our motor load, which is not dependent upon voltage, in the sense that the power stays the same, with our non-motor load, our resistive load, we can say on average if the voltage is down 5%, our total load is down about 3%. Okay? Now, when we have low voltages, the lights will dim. That's not a real major issue. But the issue with industrial loads being interrupted is a very, very important issue. I'll show in more detail how we can have serious damage to IT equipment, computer systems, electronic systems. And then another aspect is, like we said, as our voltage drops, our currents are increasing, so we have to be very careful that we're not actually overloading some of the end-use devices. Now, from a system viewpoint, low voltage is an indication of inadequate megavar reserves, and we have the whole potential for voltage collapse. So really, we have to keep our voltages at a certain level to preserve the reliability of the system and also to protect damage to equipment. In the case of high voltage, if we have excessive high voltages, we can actually have damage to insulation inside of circuit breakers, capacitors. So basically, those devices are designed to have a certain rating based upon a certain voltage. As that voltage goes up, say to 110%, we actually get a magnifying effect. We've got certain transients where the steady state voltage gets magnified with opening and closing of devices. So in general, we have to make sure we're keeping our voltages within those maximum limits, otherwise we have damage to insulation, and we can even have flashovers. Transformers are especially important to watch the voltage on. With a transformer, the actual flux in the windings is a function of the voltage divided by the frequency. So it's that ratio. So if you have high voltage in combination with a lower frequency, you're actually increasing the flux. You cause what's called a saturation effect, and you can get leakage currents and overheating and breakdown of insulation. So transformers are very expensive. They take a long time to replace, so it's very important to maintain those those voltages to not be excessive. And again, we've talked about during the nighttime or light load or restoration conditions, you can have very high voltages, and it's very important for you as operators to really stay on top of those and understand ahead of time. Before you switch any device, you need to anticipate the types of overvoltages that it may occur. We